Hi everyone, are you able to hear me and see my screen clearly? Okay. Okay. All right. So, okay, I'm really sorry, Prasant. I kind of forgot. Okay, let me just okay, so let me just try to see it after the session today itself so that we don't forget it again. Okay. And yes, let me just do it after the session today. All right, wonderful. Great. So let's start. All right, shall we start? Great. Hi everyone. All right. Hi, everyone. Let's start here. And so yesterday we were experimenting with Hadoop FS and the hands-on. So I hope everybody was able to do these hands-on. We were able to upload the data into HDFS. Okay. So I would like to do the next exercise here. All right. So for me, what I did yesterday was I uploaded some files into HDFS, right? Okay, let me just check my audio settings once if the correct audio is selected. Yes, it's the correct audio. All right. So yesterday we interacted with Hadoop and HDFS using Hue and using Hadoop FS command. Okay. Now, question from Noor is how do we do with WinSCP or PuTTY? All right, so where was the, yeah, here was the one, right? So from your laptop, if you directly want to interact with HDFS, then you could use Hue, this one, okay, this one, right? So using this, we can directly upload from the desktop or download to the desktop various files. Okay, but if you want to say interact with HDFS from Linux console, we need to log in. We need to log into console. Let me just log into Jupyter. That'll be easy. Either web console or the console within the Jupyter. Either of the two consoles would do. Okay, let me just log into web console also. So here in the web console, you have to provide the login password, but in case of Jupyter, once you logged in, it does not require again. All right, so what we have here is that we have logged into console and we can use Hadoop FS to interact with the HDFS. All right. Also, in case you would like to interact with HDFS from a remote servers, then you will have to expose the services to the external servers via the firewall, and you will have to provide the name node address in the settings of Hadoop FS command. Okay, so there are a couple of more commands in Hadoop FS. Okay, I'll just walk you over these. One is, let's say we want to append to a file, then we can use a command called append to file. Second one is cat. Let's say we want to see what's there in a file, then we can use cat. If you want to just compute the checksum, we can compute the checksum. So I'll just show you. So let's say what was the file that we yesterday uploaded? Okay, so I think this was a file. Let me just work on this file. Okay, so I can see this file from the console. I could see Hadoop, FS, cat, and this. Okay, for binary files, avoid doing cat because you can't really see it on the screen. Okay, so this is what we wrote in this file, right? And if you want to see checksum, what is a checksum? Checksum is a cryptographic signature of a file. No matter how big is the file, checksum is always of the same size. So you cannot change a file such that you get the checksum of your choice. So if there is a checksum and you want to generate a checksum of your file by modifying the file, you can never achieve that. Okay, so checksum is fairly unpredictable for a file. And if there is no change in the file, the checksum will always remain the same. Okay, so there are two checksums it had generated. One is this is the main checksum, and I doubt this is of any use. Yeah, this is the checksum that it had generated. Okay, so checksum is basically a signature of a file. No matter how big is the file or how small is the file, you will always get the same checksum. Okay, I'll show you another file. Okay, let me go to Hue. And there is a Hues file in HDFS. We have kept it for the purposes where we can demonstrate. So let's say we have, not this one. Okay, so let me see if I can recollect. Let's say this file is there, right? This is how big? 1.4 GB file, right? So what I'm going to do is I'm going to, so there is some file, really huge file. I'm going to see the checksum of this file, okay? So the checksum of this file is going to be like this, all right? So you can see that the checksum of this file is this big, and this file, the file which we just created yesterday is this. Our file was few kilobytes, right? While this file is few gigabytes, and still the checksum is of the same size. Okay, checksum is like signature. It's a cryptographic signature, meaning that you can generate the signature from a file, but you can never predict the content of a file based on the signature. Neither you can change a particular file such that you get the desired checksum. All right, so it's kind of a one-way process. You can never guess the content of a file based on the checksum. All right, so it's a one-way, we call it uh, one-way process. All right, so whenever let's say you're building a system in which you want to store the passwords of the people, you never keep the original password. What you do is you generate the checksum for the password, and you keep the checksum of the password. You don't keep the original password. Now, in case user wants to log in, the way you do is you take the password from the user and generate the checksum and compare the checksums, which means that you can always validate if the user knows the password, but you can never tell the user or anybody their password, even if they want it. So yeah, that's how we basically do the checksum. So a question from Inda is it similar to hash code? Yes. So hash code in Java or in other programming languages, there is a way of converting a big string into a small number, into a long. Okay, that's called hash code. That's quite predictable. That's quite predictable. And unlike say MD5 or CRC, not MD5. MD5 is, yeah, MD5 is a good example of cryptographic checksum. And there is SHA-1, there is SHA-2, and early before MD5 there was another one which got cracked, and it was called DEC or something like that. There was another checksum, I forgot the name. So basically you use these checksums for verification purposes. All right. A good example would be Okay. So this is the name of the checksum. Okay. This is the name of the checksum, that the one that is being used. So it's saying that it's a MD5 of this particular kind of this. So it's a checksum of checksum of checksum. All right. So it's the name of the checksum that they are using here. But I'm not really sure that, because this looks like this portion from here to here looks like a standard MD5, while this looks like a CRC. Okay. All right, Binta. Good, good. A question from, there were a few more questions. Let me answer those questions. These are very important questions. Okay. A question from Alok, is there a limit on uploading the file to HDFS? Yes. So in our case, what we have done is we have put a user limit, and the user limit is 4 GB, including all replications, which means 4 by 3 is the amount that you get. Question from Sachin, what is checksum? That I think I've answered. Question from Robin, how is checksum generated in HDFS? Do we need to set it in the system, and where? So checksum is created as part of the metadata. All right, whenever a user is uploading a file, a checksum is kept, because checksum is anyway generated just to ensure that the content of the file are intact. So checksums are kept so that in case, let's say, there is some corruption in the file, so HDFS can quickly check the content, convert it, generate the checksum, and then compare with the internal checksum, so that it will always be sure that the content of the file is intact. All right. So checksum, CRC, these are also used for these um, code, you can say the encryption, is also used to validate if the data is transferred successfully or not. Let's say I'm transferring my file to you, and then from the other side of the wire, once the process is completed, the system sends me the checksum after computing it, so that I would know that the whole file has been transferred to me back, right? If the checksum is correct. So checksum is used it at many more places than you can imagine. Like, for example, there's a command called rsync. Using rsync, you can copy the files from one system to another incrementally. Only the data will be transferred. Only the delta will be transferred. So there also checksum is used. Similarly, checksum is used in almost every protocol. Okay. So HDFS has checksum enabled by default. So it is not computing checksum when I'm calling it. It has already computed and kept it. Okay. A question from Rajan is it possible to directly edit a file that is on HDFS without doing get input? No, you will have to bring it, but you can append to an existing file. You can append to an existing file using Hadoop FS append to file. Okay. All right. So you can't use VI or Nano to directly edit files on HDFS. But an interesting part is that you can mount HDFS. You can mount HDFS as a local drive on a local folder, and you can just use VI then. All right, but it is going to be slow. All right, I think if you that could be one of the solutions. We have tried it earlier in CloudxLab, but then it was causing too much of confusion between people that where is my local drive, where is the HDFS? So we stopped mounting it, though the functionality is available. All right, good question, Rajan. Can we use cat command to see the content? If we mount HDFS locally, then we can use normal cat command. Otherwise, you can use Hadoop FS cat. Okay, it provides us the cat command and append to file and so on. All right, so okay, Now, the next question from Alok is, it is an internal process of HDFS. Is there any use case we need checksum as a developer? So sometimes while we are uploading a file, we may want to check check the checksum of a file locally and then check if there is a difference between the two. Okay, let me just check if MD5 sum, let's say MD5 sum of 17th Feb. All right. So it's actually different. No, actually, let me just copy this locally. Hadoop FS get. All right. Now then I'll do the MD5 checksum of local file. And then, so this is 737419 while it is something else here. I think it is a different checksum that's being used. Okay, so it says MD5 of 262144 MD5 of 512 MCRC. It's some other checksum that's being used. Okay, so we just need to figure out what kind of checksum is used. So sometimes while copying the file into HDFS, just to be doubly sure, we may want to see the checksum. All right, although this checksum is also used by the system. A question from Grisma is, can you repeat on copying? Okay, so the way it happens, this is a very important point, and you would use this very frequently now, because this is a technique that kind of came into production around 4 to 5 years ago. So let's say it's an important thing though. So even though it's kind of not part of big data, but you may find it useful. Let's say you have two sides. Okay, this is, let's say, the US. Okay, and this is, let's say this is Bangalore. Okay, so here you keep the backup. Here you keep the backup. Okay, you keep the backup here, and here you keep the source data. All right. All right. So what we do is, let's say this is the database file. Let's say, and this file is of few GBs here. Okay, few, let's say 100 GB file. So every day this file is modified by, say, 100 megabyte or so, and you want to take a backup of this file every day, right? So this database file will take really huge time to backup, correct? So in these scenarios, you don't generally copy the entire file. Instead, what you do is you use a tool called rsync. Okay, and what rsync does is, either this side using rsync you can pull, or using rsync you can push. Either way, what it does is, between two boundaries, this is network. Okay, between two boundaries, what it'll do is it'll basically compare backup and database file, and will only transfer the delta. It will only transfer the delta. Okay, only the changes will be transferred. Only the changes will be transferred. Okay, so basically this tool is insanely useful. rsync, the author of the tool is the same guy who designed the Samba server, and it's an interesting algorithm. So it's quite often used in synchronizing two folders, one-way synchronization of two folders, very frequently in the industry. The tool that we had at Amazon, the tool for uh, what do you say, for provisioning, used rsync exhaustively. Okay, so rsync basically figures out the delta automatically between the two remote folders, and it does it by using the checksum and advanced checksum mechanisms. Okay, so even if it's a single file, it will only transfer delta. All right, so it is really fast. Sometimes when we do synchronization, it'll take around, it may makes it around 10,000 times faster or so. Okay. All right, so this is rsync, and rsync also uses the checksum. So checksum is a very popular, very useful thing. Okay, and it is used beyond what we can imagine. All right. So a question from Noor, I heard that there is no file size limitation on HDFS. So is calculating checksum is fine if the file is big? Yes, because computing the checksum is something like unavoidable. And yes, computing checksum is time consuming, but it does not require the entire file to be in the memory. So it's completely okay to do it even on the big files. Couple of use cases of checksum for you. Um, I can actually do the whole session of the checksum. So a couple of use cases for the checksum for you is, let's say you have a big folder structure and you have copied your music multiple times, photos multiple times into that folder, and you want to figure out quickly that if you have basically duplicate files. So all you can do is go through the entire file system and then generate the checksum for each file using the find command, and then do the sorting. So that's a very quick way to find out if you have duplicate files. Okay, so a question from Robin is, at what component of Hadoop ecosystem is checksum such as MD5 installed with? MD5 is a local command which comes with Linux, and it is assumed that it has been installed on all the machines. Okay. So a question is, can we use cat to see the content? I think that I've answered. How and where we set the limit of files to upload? Is it the name node, or so checksum is used to check the content of the file? Okay. How and where we set the limit? Using HDFS command, we can set the limit. Okay, so all right, let me just minimize this. Now, using where was it? So using HDFS command, I think using HDFS admin. No, I think what was that? HDFS. So using HDFS, I think using HDFS, we did set the quotas. So somewhere we had set the quotas using Hadoop FS, or I think using DFS admin. Okay, so yeah, I think using set quota we used. So we used this command to set the quota for the users. All right. So that was I was trying to answer. So there are two commands basically. One is Hadoop FS, other is HDFS. Okay. HDFS is basically new command, does the same thing what Hadoop FS also does, and a little bit more things. Okay. So yes, it is at the name node level. This command sets the limit at the name node level. So checksum is used to check the content of the file. Checksum is used to check, validate. Checksum is used to basically check the signature of the file. Okay. Checksum is essentially the signature of the file, just to ensure that you also have the same content. Let's say I sent you a music file. I don't know whether you have received completely or not. So one way is that I ask you, can you transfer back the MP3 file, right? The other way is I can ask you, can you just compute the checksum and share the checksum with me? So I'll just compare the checksum of my file and your file. If both the checksums are good, that means the file has been received completely. Otherwise, there has been some error. Okay. So very good set of questions. Okay. Question from Grishma is that while while Hadoop FS cat, it's giving an error. It's giving a long list of commands. So what you should do generally is you should say Hadoop FS dash cat, and let's say this file I'm doing. I can put pipe and more. Okay. So it'll basically do the pagination. It'll basically do the pagination for us. So that could be a quick way of avoiding the screen blindness. We call it a screen blindness when too much of text scrolls over. Okay. A question from Subhu is that rsync is a real-time sync or batch process? Rsync is a batch process in the sense that rsync needs to be manually executed. Okay. A question is checksum does on metadata. So checksum does the checksum of the actual content of the file, and checksum becomes a part of metadata. Okay, so next question is from Noor. You mentioned that HDFS file can only be changed by loading the file on the local file system, but HDFS file is on multiple data node. What if the file is bigger than the size limitation of Linux file system? That's good, very good question, Noor. So yes, so in HDFS file system, the files could be really big. Therefore, using cat, using the other tools could be really inefficient at many points. So what you do is you write your HDFS, you write generally your MapReduce program in case the file is really big, okay, in order to only deal with portions of the text that you are interested in. Okay, so this kind of data, when it grows bigger, what can be handled locally, then you will have to use the tools like MapReduce or Spark or Hive in order to deal with it. All right, so very good question. Question from Bindao, can we use cat to see the specific range of content? Can you show us? Exactly. So again, a good question, Bintao. So basically, cat is a command that cannot show us specific range of lines. This is where the map function of Hadoop MapReduce or Spark comes into play, whereby we could say that show me only these. So we could write a map filter asking it to only display few ranges of files. Okay, so because cat and these kind of commands are very impractical if done on terabytes. Okay, all right, so let me just make a note of these things. All right, good, very good. Okay, a question from Hitendra. What is tail command but no head command like Unix? Yes, it doesn't provide the head command for some reasons, but it does provide you the tail command. Okay, tail command shows you the last few records, and I'm not sure if you can control the tail command really well, as in you can specify various options here. So yeah, so tail command is there, and you have tail dash F. Okay, does it have this? Shows the last 1 KB of the file, and dash F shows appended data as the file grows. Okay, wonderful question. Good. Or a question from David is from yesterday. There seems to be a lot of overlap between the tool. Is there a chart or diagram showing what tool can be interchanged, or how to start with basic tool and graduate to a more robust tool? For example, MySQL to HBase. Good, good. So I think I would require maybe some time to prepare this. If some of you would like to help me out with this, I would definitely welcome that part. Okay, so but this is a very important question, and probably it'll be quite useful to many people. All right, good, good. I've again made a note of it in my to-dos. All right. A question from Sachin is, can you again summarize what is rsync? Yes, definitely. Let me go back to the diagram. Okay. All right, let me go back to the diagram. Imagine you have a data center in the US where your database is there. And this database is really huge, say 100 gigabyte. And every day, let's say, 100 MB is appended to this file. Okay, every day 100 MB is appended to this file. Now, every day you would like to keep a backup of this file in your backup data center in Bangalore, for example, right? So one way is that we copy the entire file again every day. The second way is use a tool like rsync, which will only transfer 100 megabyte. Okay, and it would not keep a kind of metadata somewhere that yesterday we synchronized these portions. No, even if it's a single file, this is a single file here and there will be a single file here. So even if these are two single files, still the rsync will only transfer the changes, which will be approximately equal to 100 megabyte. Okay, so if you want to synchronize the music from your friend's folder to your folder, you could use rsync. Okay, and as a matter of fact, the author actually designed rsync so that he could happily copy music to his file, his wife's laptop. Okay, so that's what he has mentioned in his PhD, in his PhD thesis on rsync. So, all right. So basically, rsync is a very useful tool for doing a lot of interesting things, and it uses all kinds of checksums while comparing backup and database file. Okay, it does it over SSH. So if your local file system, if your remote file system is on SSH, you can do that. Also, you can execute rsync here or here. So either you could do pull or you could do push. All right, Sachin, did it make sense to you? A question from Noor is, let me, yeah. Okay, a question from Noor is, did you tell us how to upload file from laptop to HDFS? You can use Hue. Okay, you could use Hue or you could use few more tools. So from laptop to HDFS, you can use Hue. If you want to first transfer these files from laptop to Linux, you could use SCP, SFTP, WinSCP, or Jupyter. All right. So if you are on Windows, then you will have to install either WinSCP or FileZilla. While on Mac or Linux, let's say where is my terminal? Here item is there. I've installed a console here. So you can use rsync, not rsync, sorry. You can use say SCP to copy the file from local to the remote, to say e.cloudxlab.com. Okay, so let's say, let me just go to my downloads or let me just go to my desktop. There'll be so many screenshots, or which one should I do? All right, so okay, I think this one's the one that we created for, okay. So let's say we have this file called sparkr.txt, okay, and we would like to copy from local machine on Mac to my e.cloudxlab.com. How do I know it's E? When I look at my lab, this URL is this. Also, please note that here you will have to specify your login like this, Sandeep Giri 9034 at e.cloudxlab. Also, you can also You can also do, okay. So also you can use the any of the machines EFGH. The now file system is synchronized in all the systems. Okay. So what I did basically was copied the file from my laptop to Linux console. Okay, the easiest way would be using the Jupyter, because Jupyter provides you this file system, which is basically this machine. Okay, CloudxLab Linux console. This is what Jupyter presents us here. So if I refresh it, so it has uploaded. Okay, so using Jupyter also I can upload, or using SCP, or using even rsync we can upload. So between two machines we can do the file transfer the way we have been doing it traditionally. All right, so this is basically how we transfer the files between any two machines. If this is Windows, then we're going to use WinSCP, FileZilla, or SFTP. These things we need to install. While if this laptop is of Mac or Linux, we have SCP, rsync, and Jupyter, so we can use those tools. Correct. Here we are not uploading to HDFS. The way to upload directly to HDFS is using Hue, or we can also, one more way is there, that on your personal laptop, what you can do is you can install Hadoop FS command. You can install the Hadoop FS command, but then here we will have to open the name node and data nodes to the external laptop, which we have not allowed yet. But in production, in real time, what we do is here we install the Flume commands, clients, which are going to copy the data from here, or we'll just install the Hadoop FS command here and then remotely push the data. Copy from local is what we'll do, and it will push the data to HDFS remotely. Okay, did it make sense to you? So yes, Hue is not fast for production reasons. So in production, generally what we do is, let's say there is a machine which is not part of Hadoop cluster, and from there we want to push a lot of data to HDFS. So one thing we could do is we could use either Uzi or Flume, or we could install Hadoop FS command here and then copy the data from this laptop to there, if the data here is really big. Okay, great set of questions. Now, a question is Flume faster than Hue? Yes, because see, if you look at Hue here, Hue is limited by the speed of the browser and the constraints by the browser. Say, for example, we cannot upload more than, say, few gigabytes using the HTTPS upload. Okay, so it's basically constrained by what browser supports. Also, what Hue is doing for you is Hue is temporarily copying the data internally to the local disk. So what is Hue doing? Hue is first copying the data on the server on, say, e.cloudxlab, on d.cloudxlab, and then uploading the data using the Hadoop FS driver. Okay, this is what Hue is doing for you, okay, internally. So it is definitely more inefficient. Okay, when it comes to production, we generally use Hadoop FS command by installing this client on the machine which is having the data. All right, very good question. A question from Robin is, how does checksum generator interface with rsync during the process of assuring only the file changes will be transferred from local to remote? what other checksum generator is compatible with rsync besides MD5. So basically, rsync internally uses the MD5 library, and it is not compatible as such with the checksums. It has its own algorithm. Say, for example, it has normal MD5 checksum. Along with that, it has something called rolling checksum. So it has its own internal checksum as well. So there are multiple kind of checksums that it uses, and that's the whole game is about. Okay, good question. Now, so question from Sachin is, for Flume, we need to install Flume in our local laptop. That's right. Just that the remote file system, like remote name node, should be accessible to your laptop, which we have not yet allowed. Okay. So, but in case of a production environment where you know your server and you trust your server, then you will basically open the firewall ports for this laptop from your HDFS, and then you can use Hadoop FS command. Okay, say for example, when we were migrating the data from one cluster to another, then we had to open the port between the two servers. Okay, so that's how. Now, the next question could be that what would we do if we have to synchronize two HDFS file systems? For that, we have a command called Hadoop, not here, command called, we have a Hadoop, okay, Hadoop FS help and rsync, okay? I think it's a sync. Oh, it isn't. I think there was a command called synchronize. Okay, so there are quite a few commands. You must take a look at it. Okay, I think instead of fs, we had that. Okay, so yeah, distcp. Okay, so if you are copying the data in bulk from one file system to another, you could use distcp command to copy recursively the huge files from one place to another. And this is extremely fast because it does it distributively. It basically copies the data distributively. Okay, so this is specifically of great use when you are copying data between two, two different two different HDFS systems. Okay, now yes, it is between two data nodes, as in, let's say we were having an old cluster of Hadoop and we are moving to a new cluster, and this is where we use this CP. So what we did was we basically used this CP command between the two file systems, and it copied from the older to the new one. Okay, question from Hiten is rsync a Linux command. It is Linux command, but it's also available on Windows. There are many wrappers around rsync. Just look for it. There is Delta copy, there is remote copy. There are many more packages bundling rsync for Windows. As well as if you are on Windows, you can use something called Sigwin. Okay, Sigwin, and Sigwin comes up. Sigwin has the full utilities installed for you on Windows. All right. So rsync also will be made available to you on Windows. All right. So you can happily copy the music from one place to another, or synchronize the music from one folder to another. That's what I used rsync for. Okay, Sachin's question is, we can also use git bash. Yes, git bash is basically a Sigwin, a small part of the Sigwin. Okay, good. Hadoop FS and Flume is the same. No, they are two different things. We'll learn Flume soon. All right, where do I find an installer for Flume and Hue? Okay, where do I find the installer for Flume and Hue? So both of these are installed when you install Ambari. Ambari will install all of these for you. Okay, except for Hue. Hue we had to install from the internet. So you can take a look at it, installing Hue. Hue is again open source, so you don't have to worry about license fees. Okay, so you can use, this kind of a link. All right, good, good. So a question from Noor: in Windows 10, we can enable Ubuntu Linux subsystem. Wonderful. Yes, but I have not tried yet, so I'm not sure how it works. So I would love to see, because I don't have a Windows 10 machine yet. Okay, now, great, great. Now, these are a great set of questions. All right, so I hope this is clear to everyone. So please finish the hands-on assessments on HDFS. Now, let's move on to how do we find out which file is where. Okay, so how do I find out which file is where? So let's take a look at the file that I was talking about. Here, there was a file inside. Let me just check my own file first. Okay, all right, I'll tell you which exercises to do. Okay, so here, let's say this file, and we want to find out where are the data blocks for this file. Okay, so what we do is we use a command like this. Remember this command? So all it does is there is HDFS note. It's a different one. Instead of Hadoop, FS, and so on, it is basically HDFS FSCK blocks, locations, recs, and files, and then you specify the absolute path. Okay, so you can see that it has printed the number of blocks. So take a look at this. It says that connecting to name node. It's connecting to name node via the REST API because it is a URL here. So this is what it basically called. If we call it from our browser, will it work? I don't think it will work because this IP is the local IP of the server. And please note that HDFS runs on this port. Okay, so basically this command is talking to the name node at this port and asking it for the details of the file that we have asked. Okay, for the details of, for this user, the details of the path, this one. Then it is saying FSCK started by such and such user. Okay, so the FSCK is started by name node. Okay, and here FSCK means file system check. Okay, and then the very interesting thing, it says that this particular file has these many bytes and there are only one block, meaning since the file is only is really small, so one block was sufficient for this. And then it is displaying us this is the ID of name node. Okay, remember we discussed about there could be multiple name nodes and so on. So the block ID and the name node ID forms the unique ID for the block identification. Okay, so this is the block ID, and here it says this is the metadata, the size of the file, and there are 3 copies of it. One here, other here, and other here. Okay, so it says 179. I am on 179. You see that? It's the same IP address. It's the same IP address. So first copy is on E, where I'm logged in right now. And second copy is here, and third is here. To understand these IP addresses, you could go here and take a look at IP mappings. So we have listed these IP mappings, private versus the public. So this one, 37.42, last 2 digits are important. 37.42. So second copy is on D. Okay, And where is the third copy? Third copy is on this 20.58. 20.58. So first copy is on E, second is on D, and third is on G. Okay, that's what this is showing us. Okay, all right, I'll just give you the command. You can also give it a try and then take a look at it. All right, I'll talk about the exercises in a minute, Sachin. Okay, remind me in case I miss out. Okay, a question from Grishma: won't there be a virtual name used for name node, or it is accessed by the IP address always? So internally, since that's the way we want to address, we would like data node and name node to talk using the local IP address instead of using a public domain name, because we want to keep it isolated. That's why we have created them using the private IP address. Now, a question is, what is this port referring to? Okay, this is the port. That means this is the port of data node. Okay, this is the port of the data node. So as I told you that whether name node or data node, all of these are nothing but network services running in the background. So we can see that name node is running on this port while data nodes are running at this port. FSCK stands for File System Check. Good. Okay, so did I miss anything? A question from Mindao. HDFS FSCK blocks, locations, racks, files. Oh, I think the dash is missing, Bindao. Could you take a look? Dash before the files. Okay, and it's not giving me results. Just try that one. So probably, let me just try the same thing. Okay, so here we are saying HDFS FSCK locations and files. So let me see if I can access. Let's say I'm not allowed to access your files. Oh, it did allow me. Okay. So it says that these files are healthy. So how many replication factor right now? Replication factor is 3. A question from Robin. On the FSCK output shown, on the FSCK output shown, what is the name node option? What is the data node portion? The name node portion is basically it is showing that it's connecting to the name node, FSCK started by such and such person, and so on. And then it is basically displaying the various blocks. So actually, it doesn't go till the data node. It just gives you the information about the file. It just checks the files, the various blocks of the file in the metadata and prints it. It doesn't talk to the various data nodes. It just gives you the list of data nodes to who you need to talk to. Okay? Wonderful. Great set of questions. Trying to understand the output here. So this particular file did not get split into multiple blocks. It has only got replicated across 3 blocks. That's right. That's right. So far, no splitting. Okay. Just to experiment, if you want to see how does a humongous files look like. So I'm going to show you on really big file. Okay, so if I go into data, I'll have to rummage around a bit. I forgot where did I keep the okay. Should I just do it on this file? I think that'll be good. Okay, what else can I do? There was this blockchain data we had uploaded here. I think this is the one. Yeah. So it has say 7.7 gigabyte. Anybody? How big would that be? Would this file be? Anybody? So sorry, how many blocks will there be in this file? Quickly. Okay, let me just show you exact bytes and you have to tell me how many blocks are going to be there. Okay, so this is the file size, which is approximately 7.7 gigabyte. So how many blocks? Yes? Anybody? Block size is 128 MB. Yes, how must that be? 128 MB is the block. So total number of blocks, how many there will be? Let me just check. Sorry, let me just check with Python. So how much is 128 MB 1024 into 1024, right? This is kilobyte, these many bytes, right? So let me just put a dot zero so that it becomes a decimal. So you can see 62 blocks because the last one is going to be little smaller, right? So this minus 61 into 1024 into 1024. So these many bytes will be there. These many megabytes. Okay. So no, there's something wrong. Am I doing? No, we have to multiply it with 128. Okay. So last one is going to be the 110. Okay. So total number of blocks are going to be 62. 61 plus last one, right? Okay. The reason I'm doing the decimal division is exactly for that purpose. If you skip the dot zero, it'll basically do the integer division and it will give you answer as 61, right? Because integer division is basically giving you the upper one. Because if you divide 1 by 2, it won't give us 0.5, it'll give us 0. Okay. Great. So how many blocks? 62 blocks, right? Now let's try to see if our assumption is right. So we are going to do the same command. We're going to do the same command on this file. Now you see that? You see that there are 62 blocks here. Okay. So it says there are total 62 blocks, right? And the various copies are on various nodes. See that? These are various copies at various nodes. Okay. So these many blocks are there. Okay. And this is the default replication factor. As of now, this is the current status, and this file is healthy. Good. Yes. Okay. Question from Robin is in here. Okay, where did it do that? Oh, you mean when we do Hadoop FS something, right? Is that your question? Okay, so let me just show you. So when we say Hadoop FS this, so it shows us this 3. That means it has replication factor of 3. Okay, this is the total file size, and This is the permission. This is the permission. This is the replication factor. This is the user. This is the group. And this is the size of the file. This is the created date or updated date. I don't know which one it is. And this one is the name of the file. Okay, great. All right, so is everybody comfortable with this? A question from Noor, why tab completion doesn't work with HDFS command? Because tab completion is from bash, and bash always try to complete with the local file, not the remote file, right? Great. So what we learned today was the various blocks. And now let me talk about the exercises. So most of the exercises are there in the CloudxLab, and you need to go into my courses. So here you need to go to my courses and click on start. Okay. And once you come here, then let's say you have finished all these and skip this one and okay, skip this one and we have, let's say we are here, HDFS. So you can see that there are 58 pages. You can quickly skip the videos if you're clear about the concept. Okay. So whatever we talk about in the classes, we have already recorded it. Okay. And you can go to various questions. Okay. You can go to various questions. And here there are various exercises. Okay. And by the end of it, you will get a clear picture of various aspects of HDFS. Okay. All right. There are sufficient number of questions which you can practice with that will give you a very clear picture of how does HDFS work. So you will not have hesitation about experimenting with HDFS. All right. So that was a quick overview of HDFS. Okay. So around 4 projects are there. Noor. Okay. Great, great. So we actually have to do a couple of more things. One is I would like to set the replication factor, right? Also, okay. So here what we have is let's say we want to change the replication factor of a particular file. So what we can do is not here. Let me just exit the term. Now, here in this, we had Hadoop FS ls, and we had this file, right? Let's say we want to change the replication factor of this file. So how would we do that? We'll use a function called set rep. Okay. And when we say W, that means we can wait till the replication factor finishes. Okay. So this is what we're going to do. So here we are changing the replication factor of our file, which is where? Which is inside /user, right? /user/Sandeep Giri. That's my login name. And my file name was this. Okay, so absolute path we have to give. So I just changed the replication factor to 1. It is saying the decreasing number of, this is a quite dangerous command because it will reduce the replication factor to 1, and which would mean that in case at this point of time, in case one of the node goes down, my file might disappear, right? So let me just again show you what happened to my file. Okay. Okay, so how to get the absolute path? So whatever is in your home directory, prepend it, as in prepend it with your home folder. Home folder is generally /user followed by your login. Okay, all right, all right. So, all right, definitely we can share the PPT, but keep the PPT with you. Do not share with people in general. Okay. All right. In case you are sharing with somebody, just let us know that this is the reason you are sharing the PPT with somebody. All right. Now, what I was talking about is this path. So what we have done is we have changed the replication to 1, and this is the block. Now, how many nodes we have? We have around 8 nodes. Okay. So what if I change the replication factor from 1 to 10? What will happen? Anybody? So I'll just say ignore weight, just change it to 10. Okay. So it is basically doing the changing the replication in the background as 10. So let's just again see what's the situation with the file. I'll just give you the command that I just used, okay, on my file, since my file is really small. So see, if you see, it has created 6 copies so far. The file system is healthy, but it says that the average block replication is 6, right? And here it says that there is one message it would give saying target replica is 10, meaning we want 10 copies, but there are only 6 live copies. Okay, it's completely healthy. That means all the copies are available. Now you can see that there are total 6 copies because there are total 6 data nodes available right now. Okay, we can check the number of data nodes available right now by going into lab credentials. Okay, by going into lab credentials and clicking on Ambari. Okay, so how many data nodes are available right now? Okay, so it says that 6 out of 8 are started. Okay, 6 out of 8 has started. So that's what it is doing. You can see that it basically created 6 copies and told us that target was 10, but found only 6. Okay, now again, I'm going to change the replication factor back to 3, and that'll be good. Great. So this is how you can change the replication factor. Please explore the various commands. I'll just give you a walkthrough again of various commands. A question from Sachin is, I have done 48 but did not find commands of Hadoop till 48. I think towards the end, you will find the hands-on as well as the commands. Okay, so we went to Ambari to check the live data node. Okay, so actually this part is somewhere, I don't know why it shows 7, but this is what is the right one. Okay, all right, so all right, so 1, 2, 3, and okay, 4, 5, 6, and this one is stopped. So that's why. So out of 7, there are six nodes available. I think this one is stopped. Okay. So how many are there? 1, 2, 3, 4, 5, 6, 7. One of them is not having the data nodes. Okay. One of them is having the data node as shutdown. Okay. Okay. Maybe we'll take a look at it again. Okay. A question is what is the max replication factor possible? Correct. It's the number of data nodes. Because no two copies can be on the same machines. So the maximum possible is how many data nodes are available. Good. So what does it mean when I set replication only to 6, but I get 8 data nodes? Okay, if you have 8 data nodes and you have set 6, that means there will be 6 copies to the file. But so at most you can specify replication factor as 8. You can't go beyond 8. Okay. Right now there are 6 data nodes up. That's the one. Replication means will all changes be synced? That's right. If a file size is big, it is difficult to handle, right? That's correct. It's going to copy the entire data and making so many copies. So if you have, say, 6 data nodes and you have set the replication to factor to 6, there'll be 6 copies of the file. And if you are storing, say, 1 gigabyte file, it's going to consume 6 gigabyte on data nodes. Okay, each data node will consume 1 gigabyte on every data node. That's right. So a question from Grishma: in case of 1 terabyte file, will replication be done? I mean, in the real-time scenario, yes. So even if you have a terabyte file, it'll copy to, it'll make the 3 copies by default, and you can change the replication factor if you want to. Okay. And in case, let's say, you want to save some space, you might want to reduce replication factor, but reducing replication factor could lead to the corruption in case, say, 2 data node go down and you have set the replication factor as 2. So the whole data will be, that particular file will be corrupted. Okay, so Noor's question is, how do we check the capacity of HDFS? Like how much disk is available? So generally the uh, Hadoop FS, there are many commands. Take a look at all the commands here. So here there are commands like du, which tell you about the disk usage by each folder. Similarly, there's a command called df, which shows how much disk is available to you. Also, there are commands like you can check the checksum, you can change the groups of a file, you can change the permissions on a file, you can change the owner, you can copy from local as in put, copy to local as in get, then count as in, I think count means will basically, let me just see, I'm using the count for the first time. I've not used the count so far. Help, I'll say count. It says counts the number of directories and files and bytes under the path, okay, that match the specified files. Okay, so basically the count will give you the directory count, file count, and content size for each of the files that we specify. Okay, so that's a quick overview of the files. Also, we have CP. CP will copy one file to another inside the HDFS itself. Create a snapshot, it will create the snapshot, and it can delete the snapshot, older one. Then we have DF and DU. Okay, we can also expunge, as in by default when we delete something, it generally goes into trash. using expunge, we can delete it permanently. Okay, take a look at expunge. All right, empty the trash. Okay, also take a look at, say, create a snapshot. Where was the create a snapshot? Okay, so it says it creates a snapshot on our directory. Okay, all right. Okay. Now there are quite a few commands. You must take a look at these commands. Okay, there are. Let me just give you one more quick overview. So get the file, get the permissions on a file using FACL, get various attributes of a file, then get the merge, as in if you have a local file and you have a source file in the HDFS, you can find out what are the new updates in the HDFS so that you can get only the delta. Then we have make directory, move from local, move to local, move, put, rename, rename snapshot, rename, and rename directory, and then change the access control list, change the attributes, set the replication, see the stats of the file of the path, and do the tail, as in see the last few kilobytes, I think 1 kilobyte of the file, and so on. So using text, I think you can. Okay, so touch basically creates an empty file. Truncate will delete a file. Okay, and so on. So you can take a look at each one. All right. So a question from Robin regarding the file system under path. This one is healthy. Are there cases that it will show not healthy? Okay, what may be the cause of unhealthy status and how do we resolve it? Okay, if let's say there is a file which is under replicated. So what happens sometimes is that you set the replication factor of one file as, say, 1, right? And one of the node having one of the blocks of that file went down. Now that file will be corrupted and will be called as not healthy. Okay, it will be called corrupted. Okay, because it'll say that one of the blocks are missing. In those cases, you will have to delete that file and copy again from the source. So the file is basically corrupted and there is no way to resolve it. Okay, unless you know clearly that the machine which has gone down is available. So you bring that machine again back to the cluster and it will synchronize from there. Okay, a question from Alok. I'm not clear about replication. Whole copy of the file will be replicated or only blocks. So basically, if file has n number of blocks, each of these blocks will be copied. Okay, therefore the whole file will be copied. If it has 8 blocks, say you have 1 gigabyte files, it will have 8 blocks, and each of the block will have 2 more copies by default, and therefore total three replication, and therefore the file will be replicated that many times. All right. Good. So I hope this diagram should be sufficient to explain what is replication. Okay, so each file is having multiple copies. Okay, let's say here in this animation. Okay, so by default, each file is given a 3 replication. If it has only one block, there'll be 1 copy here, 2nd copy here, 3rd copy here. Similarly, for each block, the same one will be there. Okay, now in case this machine goes down, this replication factor has reduced to 2, and to bring back to the promised replication factor, it'll copy this block to one more machine. That's how the replication factor works. All right. Uh, Alok, did it make sense to you? All right, great. So what we learned today was how to do the hands-on with HDFS, and these were the various commands that we used. So a question from Grisma is that through replication, is it possible that two blocks of a file be accessed from two different nodes? Yes, that's very much possible. Okay, great. So that was our overview of HDFS. Now let's move on to next topic called yarn. Okay, it's a very important topic and we must pay close attention to it because it's going to be quite useful as we go ahead, whether we are dealing with Spark or dealing with any other things. Okay, a question is, could you explain the last slide? Last slide was, I think, thank you. Okay, so the last slide is in the replication factor one. This one, I think it's not required. Okay, we've already described this. Basically, it is the architecture of HDFS. There is name node. It has metadata. Metadata contains name of the files and the folder, replicas, and so on, right? While client basically, whosoever the client does, let's say, wants to read data, he does the metadata operations, gets the metadata, reads the data from the actual data node and goes. Similarly, the client basically comes to write the data, first goes to the name node, creates a temp file which is basically kind of blocking it so that others can't read, and then client will basically try to write the data, and in case it is successful, then it closes it. Okay, and the replication happens between the data nodes. Similarly, name node also talks to the data node for various block related operations, such as informing the data node to copy the data between them or delete the data between them. Okay, so this is the diagram that it talks about. So also here we are showing that the node could be arranged in almirahs. uh, we also call them racks. Okay, each rack is a local network in itself, so that the computers in the same rack can communicate faster than across the rack. Okay, and HDFS is rack aware, meaning you can configure that this node belongs to rack 1, this node belongs to rack 1, but these two nodes belong to rack 2. We can configure this in HDFS. Okay, so rack or Almira, I don't know. This is probably the photo of Almira. Okay, so that's what is a rack. So you can see the server rack, right? And that could give you a better idea. Okay, this is how the server rack looks like, right? So you basically put your servers there, connect them. Each server rack has the network port within it. Okay, and that's how it works. All right, so HDFS client driver divides the file into blocks, and that blocks stored in HDFS according to replication vector. That's right. those blocks are going to be stored in these data nodes. This is one machine, this is another, this is another, this is another, this is another, and data node is nothing but services running on these machines. Okay, good, good. Should we move on? A question from Robin. At what point in the process does name node command the data node to replicate to each other, and how? Can name node perform its function even without a zookeeper in the setup? Okay, so yes, so basically the name node, let's say we are changing the replication factor, deleting a file. In those cases, name node will dictate to the data nodes that delete this, increase these replication, and so on. Similarly, in case one of the data nodes go down, then name node will inform the other data nodes to start replicating a particular block. So name node gives those commands. All right, the moment a particular data node loses the heartbeat, then name node will inform the data node to do the needful. Okay, so mostly name node and data nodes work without zookeeper. It's only in the high availability it uses the zookeeper to switch between name node and standby. All right. A question from Alok. Client directly writes to data node. Yes. Okay. First write the name node. Basically, it creates a file so that other are not able to create the same file, a temporary placeholder. And then once it's done, it basically commits it. Okay. Name node doesn't write in the data node. Okay. Otherwise, name node will become the bottleneck. This is what we talked in the first diagram. Okay. So this is what we talked around here. All right. This is what we talked, that client driver talks to name node gives back the metadata, and then driver actually goes to the data node to talk to them. Okay. What happened to this guy? All right. So basically, I'll just draw this one. Okay. All right. So HDFS is not a physical device. HDFS is basically made up of two services, name node and data node. Name node is a service running on 50070 port, while data node is running on 50010 port. So both of these are services, and generally we install each data node on different machine. Okay. All right. How does name node determine that one data node goes down? By using something called heartbeat. Data node keeps on sending heartbeat to name node, and once the heartbeat is lost, name node assumes it to be dead. Okay. And question from Alok: in data node or name node, okay, where client create temporary file to another, it creates in the name node. Okay, so when we say please upload this file, using put command, it first creates a placeholder or the file, which if the other user at the same time comes to create the same file, it'll give an error saying, hey, this file is already existing. And once the user has saved the data to the client has saved the data to the data node, then it sends a message to name node informing that, hey, I'm done with writing the data, and then name node commits it. All right, so that's how it is. okay, that behaves like a transaction system. All right, Binta. So did I answer your question earlier regarding HDFS being a physical device? All right. So what does it mean by a heartbeat? Heartbeat means data node keeps on sending kind of a packet over a port, informing that, hey, I'm alive. Okay, that's basically connecting again and again. All right. So in case the client driver fails to write to the data node and then fails to confirm to the name node will, after a point of time, after timeout, it will delete that file. Okay. All right. So how is heartbeat set in the name node? Those are part of the protocol of HDFS. Okay. What's the difference between driver and the server? Driver is a command like Hadoop FS, while server is something which is always running. All right. Data commit is done by name node. Data commit is done by the client driver to the name node saying I'm done with writing to the data node, and then name node name node marks that you have successfully created the file. Otherwise, in case you don't confirm to the name node after a point of time will assume that you were not able to write data to the data node and ignore the files that you created. All right. So that's how it works. All right. Wonderful set of questions. Keep the questions coming, or maybe just drop us at email at reaches@CloudxLab, or drop them on the forum. We have a very active forum. You could come over to the forum here. Okay. So also help as in answer to other questions, other people's questions that would help you understand the topics in details. Okay, so you can see that there are quite a few questions here. All right. Oh yeah, we need to take a break. Let's take a break and take a break for 10 minutes. Back by 9:44 p.m. IST. All right, so let's start. Is everybody back? All right, so a question from Sachin: the videos uploaded in CloudxLab will be lifetime to us? Yes, we'll try to keep it lifetime. And I mean, also you're also free to download them, just that YouTube doesn't allow them to be downloaded. So you can use the third-party tools like KeepVid, using which you can download. All right. So great. So let's start. The first component that we learned was HDFS. And what we learned was HDFS uses many computers in order to provide you a humongous storage. Now, we have many computers on which we have stored data, right? We have many computers on which we have stored data, right? Now, we need to do the computation. And if you have, let's say, 15 computers running HDFS, and most of these computers are idle because they are mostly being used as data nodes. Therefore, you would want to do the computation using all of these machines. And since these data nodes on Hadoop, these data node of HDFS, they would be having the data. So it's better to do the processing of each data blocks on each of the data nodes instead of transporting the data. Therefore, we need a system we need a system to do the distributed computing. We need a system to run our programs in distributed way. This is where Yarn comes into picture. The Yarn is basically kind of an operating system under the hood. Okay, it's not used by us directly, but it is used by the tools like Spark or MapReduce internally, and MapReduce and Spark basically give us the result. So we, as engineers or developers or data scientists, we interact with MapReduce or Spark, and those interact with Yarn under the hood and give us the results. So practically, you won't be interacting with Yarn directly unless you are trying to build a framework which can do the distribution of the computing just like MapReduce or Spark or better than that. So Yarn is more like operating system. So Yarn is yet another resource negotiator. All right, Yarn is yet another resource negotiator. All right, so now before we jump into Yarn, let me just ask you a couple of questions related to the distributed computing. All right, couple of questions related to the distributed computing. Now, first question is, how much time would it take for a computer whose capacity is, which has a CPU of 1 gigahertz and has 1 GB RAM, although this information is not too useful. Okay, so it has a single core, and this computer is being used for resizing 1 million profile pictures. So we are trying to resize, as in we are trying to process these million pictures using a computer which has a single core or single CPU. And if it takes 20 milliseconds to read the picture from the disk and 5 milliseconds to resize it, so how much time it is going to resize 1 million pictures? These are basically profile pics, and we would like to resize them. So problem statement is, I mean, this is a very practical problem statement, and we basically were doing this exactly this in case of Amazon's product images. Okay, and that's where we were doing this computation. And interestingly, I had to explain that this is what the parallel computing is. That's where this question comes from, because it was a surprise to me that my team did not know that did not know the answer to this question. Okay, though the answer to the question is really simple, but since we haven't done this kind of thought through, so this comes as a surprise. So let's say while we resize an image, we read the image from the disk into the memory, and then we resize it. So reading takes 20 milliseconds, and 5 milliseconds is taken to resize. So each picture, if we do it sequentially, will take 25 milliseconds. Now, question to all of you is, what will be time consumed in resizing 1 million profile pics? 25 million milliseconds. Okay. All right. A very good question from David. David, what is the right time? Okay. Basically, I did not want to make the problem a little more complex, but that I'll come back to later. For now, we can just say that the right time is very small, just for the discussion sake. But that's a very valid question, because right time is the one which takes the maximum amount of time. All right. Okay. So one answer is 25 million milliseconds. Okay. Any other? So for now, let's just ignore the right time and then we'll talk about. Okay. Question from Rajan is, but can this be done in parallel? Yes, that's the hardest question that we are trying to answer. So it has a single core. Can it still be done in parallel in some way? Okay. So actually, it will take 20 million milliseconds, not 25 million milliseconds. Okay. So it'll actually take close to close to 20 milliseconds to read the pic. Okay, so it'll close to take 20 millisecond for each image, so which means 20 million millisecond, which is close to 5.6 hours. Who got the answer right? 5.6 hours. Okay, all right, let me explain. So actually the 5 milliseconds that are being taken to resize an image can be ignored because that part can be performed in parallel. Imagine that you have two resources, one is CPU, other is the disk. While the data is being read from the disk, during that time CPU is sort of idle, and most of the CPUs allow execution of such processes in parallel. So while the second picture is being read from the disk, it would parallelly start resizing the first one which was read. Similarly, when the third picture is being read, it will start processing the picture 2. And similarly, it will start reading picture 4 and then resizing. All right. Okay. So what we are saying is that we can do two things in parallel. We can do two things in parallel. On one hand, we can read the pictures in parallel from the disk, and on other hand, we can resize the image. Okay. So we can run two threads in parallel. One reads the data from the disk and other resizes it. Okay, question from Noor is, if there is a program which is reading the file and resizing it, then these steps would be in the sequence. That's correct. Therefore, we might have to rewrite that program. And therefore, why most of the distributed computing is done by rewriting most of the code. Okay. Okay, does it make sense to you? So in parallel, this will be done in parallel on a large scale. Alvin, Alok, Bintao, David, Gaurav, Garvin, Grishma, Hitendra, Jay, Noor, Prashant, Rajan, Robin, Sachin, Subbu. Okay. So a question is, what does it mean by thread? So most of the programming language provide you most of the programming language are providing you this concept called a thread, using which you could do two things in parallel on the computer. All right. So, all right. David, does it make sense? Is it calculation right? Or am I missing something here? So I'm saying that instead of 25 million milliseconds, it'll take 20 milliseconds, 20 million milliseconds, just that there will be one extra time, 5 millisecond extra time, because the last picture, the picture number 4 in this example, will take some extra time, right? So that 5 millisecond will be extra. So it will be 5.6 hours plus 5 milliseconds. Wonderful question. That's what I was coming to, Alok. So one other thing that I observed in case of my work at, say, Amazon. Okay. All right. So 1 by 50 is the 20 milliseconds. Okay. 1 by 50, because a millisecond is basically 1,000 seconds. 1,000 millisecond is equal to 1 second. Okay. That's right, Godwin. So basically, reading the first pic 20 milliseconds, reading the second pic 20 milliseconds, while the reader reads the second pic, the CPU works on the first pic. That's right. So even though it is a single engine, these tasks appear to happen in parallel. That's correct. So basically, most of the CPUs are able to give you this parallel computing, because while the data is being read from the hard disk, the CPU is comparatively comparatively very free. It's not busy while reading the data, because the most of the time is being taken by the disk. While the disk is rotating, the data is being captured. At that point of time, the CPU is largely free. Okay. So question from there was a couple of more questions which I would love to answer. Okay. All right. Could you confirm, David, is the calculation right? And so what we are saying is everybody convinced that it'll take 20 million milliseconds? 20 million milliseconds for 1 million images, because each image is taking approximately 20 milliseconds, not 25. Okay. Wonderful, wonderful. So there are a few more questions that I would like to answer. First question was from Robin. In big data scenario, what program is utilized in reading the file and resizing? Here, it's our own code that is doing the resizing, and reading the file is also being done by our own code. In real-time scenarios, reading and resizing are the two tasks that are done by the same programs in general. Okay. Now, question from Alok, but we have to keep a queue in between the two threads. Yes. This is another idea that I wanted to explain to you. Okay. And what I found is that this leads to a far better design. One way is using the standard threads. Okay. Other is by using an in-memory queue. Okay. There are many queues. So we used a queue from Java. It's called blocking queues, but there are many queues available. One of the queues that I recently came with is called ZMQ. It's called 00MQ. So there are many queues available to you. You can use either of the queues. So it's a blocking queue in the sense. So we generally create this construct called blocking queue. And on one side, we have producer. Okay. We have producer. And on other side, we have consumer. All right. So on one side, we have producer. On other side, we have the consumer. So what producer does is it reads the data. In this case, it reads the data from the disk. If this is our disk, which is rotating, so this one is basically reading the data, reading the image and putting it into the queue. Okay. So it's basically, this is an in-memory queue, which has limit on number of elements in the memory. Okay. So something of this sort. Okay. So basically, this producer is reading the files in parallel and the consumer is resizing them. Okay. So consumer is basically resizing. This is in memory. Okay. So, all right. So this was an interesting concept that we did at I did at Amazon. So we basically created this kind of a framework in which people only need to define producer and consumer. Rest of the system is taken care by the framework. Okay. So what we did, if you have to design a similar scenario and really highly performant system, you will use a blocking queue or in-memory queue, or maybe one of the queues like Kafka or other kind of queues, and use the producers to read the data and put it in the memory. So you create an object of the image and put it into the queue. On the other side, there are the consumers who is going to resize the data. And then, as somebody asked earlier, you will also have like second queue, okay, in which after resizing you will put, okay, after resizing you'll put into the queue, and then here you will write the data, okay, and this is reader. So basically this one is a thread, this one is a thread, this one is a thread, and this one is a thread. All these things are happening in the thread. So this is one thread, second thread, and third thread. So there are these three threads. All right. So instead of creating so many threads, what you do is you create these blocking queues. Okay. Now, these blocking queues are very interesting concept. If the blocking queue is full, this will wait. Okay. So producer waits when queue is full, consumer waits when queue is empty. Okay. This is a fixed size. This is a fixed size blocking queue. Because you don't want to overflow your memory of the system, therefore you define the fixed size blocking queues. In case this queue is full, that means producer will wait. That means there will be no longer parallelization. While if the queue is empty, then consumer will wait. Similar is the case here. And again, yes. Can we use multiple consumer? Yes, we can use multiple consumers also. Okay. If we have multi-cores in this system, we can use multi-consumers. So those were the smart system that we built. The system was automatically deciding on how many consumers we can create, how many producers we can create, and so on. So this way, the system automatically, based on the resources, was deciding on various consumers and producers. All right. Does it make sense to all of you? So reader reads from the disk, and reader is the producer and is putting it into the queue. If the queue is full, reader will not read from the disk and wait for it to become empty. And then if the consumer is trying to consume, if it's empty, then consumer is who? Resizer, the one who is going to resize our data. Similarly, for every queue there is so this consumer is a producer for this queue and writer is the consumer. Okay, a question from Sachin, can you show the code? I don't have the code for this, but I can definitely give you an example. If you want, we can write the code for this. All right. So it's pretty simple and yeah. All right. Is it good? Everybody is clear about it? All right. So that way of implementation is what we do when we need to do the implementation on a single computer. Okay. Now, my question to all of you is, here, okay, one more thing that we missed. I created a extra system as opposed to what we discussed. This is a writer. What it does is it writes whatever we have resized. Okay, this is not part of the question. All right. A question from Robin. Where and how do we set the fixed blocking size? So we generally, while defining the blocking queue, while creating the blocking queue, we generally define the size. Okay, it is similar to the in-memory location, that's right. Is it manually or automatically set? It's basically defined at the time of defining the blocking queue. So when we say new blocking queue in Java, there we can specify how many elements do we want or what size do we want. Okay, the design can be used for larger files, say gigabytes. So question from Alok is, can this design be used for larger files, say gigabytes? Not really. Okay, because it kind of will overflow the memory. Okay. And to resize gigabytes of size files, we will at least need that much in memory space. In that case, if you are expecting the gigabyte kind of files, what you can do is decrease the blocking queue size to 1, okay, so that that can be done in parallel. All right, wonderful. A question from Noor. Why did you call it parallel computing in your slide when it is just one core and CPU? Isn't this time sharing rather than parallel computing? All right, it is basically time sharing, but all of that comes as part of parallel computing. Okay, because the same design can scale to multiple cores and so on. Okay, the principles remain the same. Okay, I think somebody has answered it pretty well above. I think, okay. Okay, a question from Grishma is, can single core, yes, core can run 2 threads in parallel because CPU will be most likely free when the data is being read from the disk. Okay, and therefore you can continue to do the parallel computing even with a single core. Now, my question to all of you is, can this be improved if we buy a quad core? If we have dual core or quad core machine, can this be improved? Anybody? So let me just go back to the previous slide. So there are 2 things that are happening here. And who is the bottleneck? Who is the bottleneck in this diagram? Who is the bottleneck here? The bottleneck, the main time is being consumed in what? Because why this 20 milliseconds? Okay, it is in the reading from the disk, correct? So it's not the CPU that's the bottleneck. It is the disk speed which is slow. So who is the bottleneck? The disk is the bottleneck, right? Because the output, the time taken by overall is independent of the time taken by the CPU. Therefore, the bottleneck is the disk, is the weakest link in the process, is the slowest link in the process. So disk is what is consuming the time, right? So, so do you still think that can this be improved with if we buy a quad core? Yes and no? Correct, Hitendra, and correct, Godwin. Yes. So therefore, even if we buy a quad core, even if we buy a quad core, it will not improve the process. Next question is, can this be improved if these 20 if these 1 million pictures were located on multiple machines? Okay, correct. In case these 1 million pictures were located on multiple computers and we did this processing parallelly, let's say out of 1 million pictures, we have, let's say 100 node cluster, and we have 10,000 pictures on every machine. And we do this in parallel, right? So if we have 10,000, so if we have, say, 1,000 machines, okay, let me say 1,000 machines, okay, each having how many? 1,000 picks. So our overall time would be if we had 1,000 machines and the pictures and each one is having 1,000 pictures, so how much time will it be? It'll be 20 milliseconds, right? It'll be 20 seconds, not 20 milliseconds. It'll be 20 seconds, basically divide by 1,000. It'll be 20 seconds, I'm sorry. Okay, so 5.6 divide by 1,000. Grishma, it won't be 25, it'll be 20, okay? All right, so that was the power of distributed computing. And what we are going to learn is how do we divide the work onto multiple computers such that we are able to achieve this. So we just proved that in many cases where disk is the bottleneck, even if we have SSD is also a bottleneck in many cases, right? Okay, so even if we have say so even if we have multi-core computer, still we won't get great results. So no matter which GPU we buy, I mean, you must be seeing these a lot of this marketing agenda these days, that you buy the CPU, GPU, and so on. But in reality, in most of the systems, CPU is hardly, except for graphics and deep learning kind of scenarios. Other than that, mostly the CPU is the most idle resource. Okay, CPU is most idle resource. And in case of big data, when you have processing humongous data, the first bottleneck is the disk read speed. Even if you have SSD, the disk read or write is also a bottleneck. All right. So a question from Godwin, that multi-threading is a process of dividing work. Multitasking is handling the work load by a single CPU. Parallel computing is handling the workload by set of CPUs. So parallel computing is by set of CPUs either on the same machine or different machines. Parallel computing is in general means that how do we get the work done in parallel? All right. So even though in this case, it was very clear that it's multitasking, but the principles remain same. Principles remain same in case of multi-threading, in case of parallel computing or multi-threading. Okay. So a question from Noor, in general, how do we generally audit a process program to know what is the bottleneck? Example, any program or monitoring software is there which can audit a process and let us know time taken at different resources, and we can draw a critical path and improve the solution by adding correct resources. A very good question. Very good question. So generally, there are many instrumentation processes. So what we do is the debugger actually, most of the debuggers actually, you can always instrument them to give the timestamp on every function. All right. Some of them provide it, but in our case in Java, what we did was we actually used our own service to document the time taken in every process. So we had a central time counting service which we had designed, in which every function's time consumed is reported to a remote service, just like logging system. So it was a logger designed specifically for keeping track of time. So that's basically what we use instead of instrumenting it. Though there are techniques of instrumenting a piece of code, that how much time is being taken by a particular program and so on, we could generally run a program through a debugger, and debugger will report how much time is taken by every function. All right. And then we do the bottleneck. General thumb rule is, okay, the way, let's say, look at a process, and so what you do is, as a quick thumb rule, you have, say, 4 processes, 1, 2, 3, 4. Okay, and so you have, let's say, for now, let me just take 2 processes. Let's say you have part of it is 1 and 2. So what you do is you do a rough statistics on part 1 and part 2, that how much time in general part 1 takes and how much time in general part 2 takes. Okay, and then you count how much is the current program taking from here to here. Okay, if this one is equal to the max of 2, if this one is the overall program that you have designed, if your program is taking closer to the max of the 2, right, that means that your program is perfect. Okay, if your program is taking the time equal to max of the 2, you will generally report that my program is perfect. Okay, so if the your program is taking more than even the sum of the 2, therefore there's a need of humongous need of optimization. So this is how we generally reach to a point that you cannot improve a program beyond the max of one process. All right. So in a black box process, you can actually instrument. There are ways to instrument a code. I need to recall the instrumentation software that we have used in past. It has been quite some time when I used Java last time, but I don't know about Python. There would be some tool in Python. GDB generally reports that information. You could actually instrument each part. All right. So great. So coming back to it, so to achieve Okay, so to achieve the let's say in a program, if there are 3 phases or say n number of phases, if your program is taking time to process equal to the max of the process, max time taken by individual part, that means your program is just perfect. You can't improve it beyond by doing the parallel computing. Okay, maybe you can break down a big part and then try to notice it. Okay, so that was one thing I discussed. Is that what you want me to repeat, Godwin? Name of the tool, I need to figure out. There was in Java, we had something. In C, GDB supports that debugging information. For C and C++, I just need to take a look at it. It has been quite some time. Okay. A question from Sachin. Can you repeat how it takes 20 milliseconds? Okay. All right. So basically what we did was, so while the data is being read from the disk, okay, while the data is being read from the disk, at that time parallelly, the so first picture will be read, that time will be taken. Then while the second picture is being read, in parallelly, the CPU is working on resizing it. That's why that's why this work is happening in parallel to what parallel to this parallel to reading from the disk. Okay, so you can think of it like this is timeline, this is the timeline, and these are the various resources. Okay, so you generally draw all the processes on timeline, and that's how you generally estimate the overall time taken by the process, just like you do in the movie production. In movie production, you have tracks, soundtrack, audio track, then music track, then voiceovers, then background music, a background noise or whatever. So they all are put on top of each other. So while timeline remains like this. So we generally do the storyboarding like this of a program if you have many different phases. Okay. All right. So that was a quick way of looking at parallel computing, and it's more like using threads. But since in our case, we were doing this on, say, hundreds of computers at Amazon, so therefore it was far more related to the parallel computing. And we had like 20 parallel phases here. Okay, so coming back to it, so now this is achieved using earlier in Hadoop 1, this was achieved using MapReduce. How to do it, how to do something using many computers. All right, I'm going to give you an overview of MapReduce 1.0, which was earlier the older way of doing it, because it's simple to explain, and then we will go into the Hadoop 2.0. All right. So the way it works is in Hadoop, remember we had name node, data nodes, and so on. So in Hadoop 1.0, what they did was they created something called a job tracker. This is again a process which is running there. And then on each machine where data node was there, task tracker was installed. So task tracker was there on every machine which has data node. Although it was not mandatory, but it is a very important as in it's a very important decision to keep task tracker on the same machine as the data node. Now so here the why does it not show me the okay, so here the end user like me and you, they will submit their job to task tracker. So we'll talk to the task tracker internally will distribute the work. Sorry, I'm so sorry, I'm just using the wrong terms. So me and you will talk to the job tracker. Job tracker is the owner of the job, just like supervisor of the job shop floor. when you go to a supervisor, you say, hey, I want to get this chair built, then he will say, okay. He will basically divide the work into multiple tasks and get that done. So similarly here, so we are ordering job tracker that, hey, we want to get this images resized. We want to get these images resized. So what it'll do is it'll go to the task tracker, various task tracker, and say that, hey, can you resize these 1,000 images? Can you resize these 1,000 images? And can you resize the third set of the 1,000 images, and so on. Now, these task trackers will pick the images from the same data node, okay? And basically, job tracker will tell that you will process only these images which are located on the same data node. Similarly, it will tell this that you will process only these images which are located on this task tracker, on this data node. So all these task trackers are reading data from the same machine without reading the data from another machine. Okay, so that's how the task trackers work and job trackers work. Okay, so basically there are two things we did here. Number one, we utilized the CPUs of so many machines, right? Also, we utilized their discrete speeds in parallel. We utilized their discrete speeds. So this is what the MapReduce 1.0 was. Okay, the only way to talk to this kind of a system was using something called MapReduce. We will write two kind of functions, mapper and reducer, and each task tracker will first execute mappers and then reducers. Okay, so each task tracker will first talk to the data node. Sorry. So we will submit our job. We'll submit our job in the form of map functions. The map function will have the logic of resizing. Okay, so it'll go to each task tracker and say, hey, can you execute my function, the resizing, and the reading will be done by this node itself, as in task tracker itself, and will resize the data, resize the file. So this was the way of MapReduce 1.0. The downside of this approach, although the parallelization was perfect and so on, but the only kind of work you could get done was the map and reduce. You could not get anything else done. Therefore, the framework was doing two things. One, doing the map and reduce kind of work, okay, as well as taking care of the resources. So this is where Hadoop 2 came into play. So earlier, MapReduce framework was doing too much of heavyweight lifting. One, it was tracking resources. It was keeping track of which machine is doing what, which machines is free, how much RAM is free on each machine. So one part was doing the operating system work, and the other part was doing the framework work, whereby execution of functions, execution of maps and reducing, sorting of data, and so on. That work was also done by the MapReduce. So MapReduce was kind of a monolith. Monolith means made out of a single stone. So MapReduce was doing too much of work, and therefore there was no scope of innovation there. Okay, we'll talk about MapReduce. Basically, in the distributed computing world, we generally write two programs. One is called map and the other is reduce, and we hand it over to the framework like MapReduce, and MapReduce internally executes those. So MapReduce here, we are referring MapReduce in two ways. MapReduce is also a programming paradigm in which we write these logic of how to transform data and how to combine data, right? We write those logics. We do not define the order in which things to be done. We let the framework do that. Here, MapReduce was also the name of the whole component, just like HDFS. Here, MapReduce was also the name of the component. We used to call it Hadoop MapReduce. Now, this big component of 1.0, MapReduce 1.0 was broken into MapReduce 2.0 and Yarn. So this big component, which was tracking the resources, doing all kinds of executions, doing sorting of data, and so on, it was broken down into pure MapReduce, which was doing the framework work, and the resource manager, the one that does the work of an operating system. All right. So that MapReduce remains just as one way of writing the program, it leaves the space for other kind of systems. Okay, so Yarn became a very generic system that could be used not only by MapReduce kind of system, but any kind of system. That opened the doors. That opened the doors to so many different systems. As of now, Yarn, on top of Yarn, other than MapReduce, you have Taze, HBase, Storm, Giraffe, Spark, and the OpenMPI and so on. There are so many systems running on top of Yarn. Just like if you buy a server, right? You buy a computer and you buy it from Oracle, and Oracle says that it can only run database. Okay, you can't do anything other than database on this computer, right? It was this same kind of architecture that we had MapReduce, but the only thing we could do was map and reduce on it, right? So even though we have like so many computers available and we would like to do all kinds of things, but the only framework, that distributed framework that was there, was MapReduce. So it was broken into two parts, Yarn and MapReduce. MapReduce did exactly same thing what earlier it was doing with respect to programming model, in which a user submits the map function and reduce function. So submits the job to MapReduce, MapReduce talks to the Yarn and get the work done, while it left space for more innovation. And this is where more innovation came into play. Today, the Spark is actually more powerful than the MapReduce. So because of this splitting, the Spark is able to run on top of Yarn. Okay, that's the beauty of it. So basically, had this not been there, as in had this older system would be there, the Spark would have actually replaced the entire Hadoop. People could have used something else. Okay, so that's the important part. So only this part is competed with Spark. So here you write something called map function, reduce function. Here you write something like a hues, a sequence of transformations, and then submit it. So the philosophy remains same, but the implementation is very much different at both the places, although philosophy is also a bit different in both the cases. But the important part to understand is, because of modularizing it, because of refactoring, we call it refactoring. Refactoring is a process in software engineering where one big piece of code is split into multiple parts, multiple independent parts, so that those independent parts could be used with other systems, right? So this was basically a classic example of refactoring MapReduce 1.0 into MapReduce 2.0 and Yarn. Okay, so here this led to so many other systems. All right, now, okay, so Yarn led to other kind of frameworks, other kind of programming models than MapReduce. It gave us it more scalability. It was compatible with MapReduce. So if you had written Hadoop 1.0, wrote code for Hadoop 1.0, the newer would already work. It improved cluster utilization because it gave more space for more kind of work. And it also improved the agility. So this way, it led to more kind of workloads than the batch oriented, right? So in Yarn, the system was a little bit more complex than what was there in MapReduce 1. MapReduce 1, there was job tracker, task tracker, and each work was executed inside a slot. So this was job tracker was broken down into resource manager, application manager, and timeline server. Task tracker was basically replaced with node manager, and so on. So this is the architecture. A question from Noor: who does the resource management of HDFS component? HDFS basically takes care of itself. Name node and data node combined together take care of their own data management. Okay. All right. So Grishma's question is, won't it be the name node which takes care of the data management? Yes. So name node takes care of the data management, but it also orders the data nodes to do various kinds of management. So data node as well as name node both participate in the data management. All right. So question from Robin. I'm curious if ever I'm tasked in future with a local framework setup of distributed computing, where do I find MapReduce, Yarn, and HDFS installer, which I need to install? Are they all free? Yes, they are all free and open source. Again, this is actually far easier than it looks. Okay, it's actually installing the entire cluster is actually really simple. Okay, just that it'll take much time to do anything. Okay, so I'm going to just give you one example of the guide. So instead of installing each of these components by yourself, I always recommend this, not this. Okay, so all right, let me just give you the. So it's actually far more simpler than it looks. Basically, all you need to do is have all computers ready. One of the computers you put Ambari server and then let Ambari install for you. If you don't like Ambari, if you don't like Hortonworks and you would like to go with Cloudera, use Cloudera Manager, which does the same work as Ambari do. Cloudera Manager will install everything in the cluster. All right. Go ahead, Anur. What happened to them? Is my internet so slow? Okay, so let's take a look at this one. So, all right. So you can actually take a look at this one. It gives you the full PDF version of it. Okay, and use that. Okay, so that was, just follow that. It kind of takes you through the entire installation of the cluster. If you want to install, just go through this process. I really liked this process of installation. Okay, you get ready, determine the stack compatibility. It takes you through the entire process of installation. Okay, a question from Noor. Um, in your slide number 8, MapReduce directly talking to the data nodes and not through the HDFS. So yes, basically MapReduce takes the information about the blocks from the name node and then reads the data from individual data nodes. Okay, it reads the data from individual data nodes and processing that data. There's the beauty about these frameworks like MapReduce and the Hadoop. Okay, so So in practical, does Yarn talk to data node separately or goes via HDFS? So Yarn basically asks HDFS. So when we submit a job to Yarn saying that, hey, can you execute this program nearer to this particular file? So what Yarn does is Yarn goes and asks name node, hey, this, do you have this particular file? Okay, where did my, okay. So that's what I'm going to do, going to talk about. So here, so even in this case, right? Even in this case, so you will say that, hey, here is my job. Can you execute it? Now, job tracker will go to the name node and ask, hey, this particular file, do you have this file? Name node will say, yes, we do have this file. Can you tell me which machines have the the blocks, which machines have this data block? So job tracker will find out, okay, these are machines having the data blocks. So it will ask all these task trackers, can you execute this process nearer to the data block? All right, that's what it does. So this is called data locality. All right, data locality optimization. All right. Okay. All right, let me just explain this once again, and you'll get a picture of it. Okay, so basically here what we are talking about, the individual task trackers is going to read the data block and process that. Okay, it can directly read the data block. So it's kind of, you can say that it's not using the general process. Instead, it's asking the data directly from the data node and processing it then and there. Correct. So question from node is, the data block is not meaningful until it get combined and become a file. Very good question. Very good question. So it's a very important question. So we'll actually talk about this, but in case we have a little bandwidth, so I would like to answer this question. Is everybody on the same page? So question is that we're talking about processing individual data block. Okay, let's say we have something like this, right? And we are processing on top of it, right? We are processing on top of it. Okay, so imagine that we had a big file. We had a big file like this. Okay, and we cut it into pieces. Okay, how can I cut it into pieces? Imagine that. Okay, let me just make it look like a file. Okay, let's say this. Okay, let's say this is our single file, and which has three parts. This is part one, this is part two, and this is part three. So basically, imagine that they have been, okay, I think you can't move them separately. So this is the third part. This is the second part. This is the first part. These are the three blocks that we have saved in the disk. So this is one, this is two, this is three. Okay, so we have these data node. This is one data node. Okay, and this is another data node, and this is another data node. All right, we have these three data node, and these three data node are having these three blocks. Okay, now question is that this block in itself is basically raw data, because imagine that it is a file, big file, and we have cut it into parts. Correct, we have cut it into parts, and we would like to um, let's say process these this big file, right? So the processor that we write basically should be able to, process individual portion of the file. Okay, say it's a big text file, so some lines would be here, some lines would be here, and some lines would be here, correct? But there would be some lines which will be on the boundary, correct? So what it does is it transmits that boundary data from here to here, okay, and then does the processing. So the only data that we can process parallelly, okay, is the one which is complete here. The one which is on the boundary will be transmitted to other machine. All right, this is called input format, and we will learn about input format and input splits as we go ahead. All right, so this raw data is converted into meaningful data in parts by using by a library or by a class or by a module called input format. So input format converts this into input records, which are meaningful here. And that's where the design of input formats are very important. Okay, we'll go into more details about this. Did it make sense to you, Noor? All right. Say, for example, there is a zip file. Imagine there is a zip file, .zip file, and it is it has 3 blocks. Then a zip file you cannot really use in a distributed fashion. Therefore, zip file is something that we will not use in case of HDFS. We will use alternatives to zip file, which are more sensible and which are splittable formats in which each part can be processed independently. Say if you are processing a text file, some of the lines on one machine, some of the lines on another machine, and some of the lines on a third machine can be processed. Okay, so we'll talk about different formats which are splittable and which are not splittable and which can be processed in parallel and not parallel. Okay, so I think yes. So there are many formats that are not great for tools like Hadoop because they are not splittable. All right, very good question. Very good question. So, all right, a question from Sachin. So Yarn support multi-threading, multitasking, and parallel computing? Yes, Yarn support parallel computing, and internally it is okay. A question from Hitend, are text file most easy to work with? Yes, generally text files are most easy to work with. Okay, and we'll talk about something called sequence files, which are nothing but key and value. Key is the name of the file and value is the content of the file. So sequence file can have hundreds of files together. Let's say we talked about processing the profile pictures. So we'll generally create one single sequence file by combining all of the all of these profile pics, and then we can process that also parallelly easily. Okay, so we'll talk about these things. We are just moving a little ahead of ourselves, so we'll as we go ahead we will get the clear picture. Okay, so yes, so parallel computing is hard and we need to be careful because not every format can be dealt in parts. Okay, so we'll try our best such that we can process individual part parallelly using multiple computers. All right, very good set of questions. Great. Now let's try to understand, how does yarn work? How does yarn work? So yarn is okay, let's say you have a cluster which has one computer, which has, let's say, 4 computers. Okay. On one computer, we will install a service called Resource Manager, while the other machines will have node managers. Okay, so Resource Manager is like your job tracker. Node managers are like your task tracker. So the client will talk to the Resource Manager and ask it to get the work done. Resource Manager will talk to the node manager and get the work done. All right, now a little bit more details. So Resource Manager basically is a singular entity. It's a central agent. It and manages and allocates cluster resources. Okay, it's important to know the meaning of these services, because if you are using a big data cluster, you will encounter these terms again and again. And it's important to know the meaning of each one, because that's how you will be able to debug what's wrong with the system. Okay, so you as a client will talk to Resource Manager. Resource Manager will consult the node manager, and Resource Manager will ask the one of the node managers to start the first process. This first process is called App Master. Per application, like somebody is running Spark, somebody is running MapReduce, per application, it will create the initial process, which is the App Master. Further, the rest of the work of the client will be done by the App Master. App Master will take the position of the client afterwards. Okay, so then App Master will ask Resource Manager, give me this, give me that, and then Resource Manager will delegate the work to node managers and get that work done. Okay, so node manager is installed one per machine, meaning all the data nodes that you have, you will generally install node managers on each of the data nodes. Okay, so it manages and enforces all the things related to the node. So node manager is the owner of this one. Okay, while we have application masters, application master is what? These are basically tasks. Okay, when when a client submits a request, application master is created. This is a running process. It's basically a process that's created, and this app master further does the work on behalf of the client. Okay, app master could be one for MapReduce, one for Spark, and so on. Okay, now before we jump ahead, you can see there are containers. In one container you have app master running, in other container you have some work going on. Okay, so the role of a container is a process, just like JVM process, Java process. It runs the user's work and it enforces the security on the client's processes, like like the memory consumption, like resource access, and so on. Okay, so I think I'll come back to this one again. Let me just go through it. Even if you don't get it, don't worry. I'll just go through it once and then come back to it again. So here is the flow. A client like me and you will submit the work to the resource manager. Okay. And the resource manager will launch the application master in one of the containers. We'll ask node manager, can you give me a container? I'll give you a container, and inside that it will launch the application master. Then the application master will kind of behave like a client and will register itself with resource manager, and the client can monitor the progress of the work by monitoring the application master. Then application master will start asking, give me more containers because I need to get work done. The actual work is done by the container. The image resizing work that we talked about will be done by these containers. All right. So resource manager allocates the containers by consulting with node managers, and then node manager launches the app inside these containers. Okay, the resizing work will be done by the containers. Okay, node manager talks back to the resource manager about the resource usage and so on. So clients talk to the application master for the status. Now, even if you did not understand anything from it, let me just explain it in these terms. Okay, imagine that yarn is a country, and each individual data node on which we have installed node manager is the state. Each node manager is like a state. Okay, and the client is, say, a company like Shell or a Microsoft. They want to get some work done, so they want to establish an office, they want to get some work done, and the resource manager is the president of the country. Okay, so the sole idea is, yes, to bring the compute to the data rather than transferring the data in order to get the computation done. That's right. Now, let's take a look at this architecture. So imagine that Yarn is a country, your whole data center is like a big country in which the president is the resource manager, or resource manager is the president, and each individual data nodes, we have installed node manager on each of these data nodes. Okay, and the node manager is like the governor of the state. Okay, so each machine is the data node is like a state, and node manager is the governor of the state. Okay, now, so node manager being the governor we will be consulted all the time to get something done inside the state. So node manager is the main authority to talk on behalf of the whole machine, whole node. Okay, now the client like Microsoft would like to establish office where there is more of software engineers, right? So it'll say that, um, can you I mean, can you get this much work done nearer to the cities which have more software engineers? Okay, while Shell will say that, hey, I want to get my work done nearer to the oil fields. Okay, or there could be another company which would like to get their fishing done nearer to the cities which have fishes, right? So basically the sole idea is to to get the work done nearer to the resources. Okay, so resource manager will tell Microsoft that, hey, before coming to my country, you need to establish a head office. Okay, that's what the president says. So the resource manager will tell the Microsoft, okay, hey, we need to create your first office. We call it head office. So for Microsoft, this is the head office. We call that application master. Same is the case with Yarn. So we have these head offices, and head offices are the single entry points for the rest of the process. Now further, on behalf of Microsoft, the head office will behave, right? Then this head office will say to the resource manager, hey, can you give me maybe 3 more offices, 2 nearer to this machine, 2 nearer to this particular state, and 1 in this state. So the resource manager will consult these node managers, and node managers will create these offices. Okay, and these state offices are are, are supposed to honor the state rules. Okay, that's why they are created inside the container. Container is nothing but like an office boundary. So app master, which is the head office, will ask resource manager, can you get my work done inside on these computers? Okay, on these machines which are nearer to my data. All right, this is how the system works. Okay, similarly is in the case of Shell, the first an application master is created, the head office of sales, head office of Shell, and then That head office further requests for more containers by talking to the resource manager, and this way it's more like our country. So it can execute all kind of things. So please note that here the Microsoft could be MapReduce and shell could be Spark and so on. So it doesn't necessarily mean that these companies exist, here, meaning MapReduce or Spark does not need to be installed upfront in the cluster. It will be installed automatically inside the app master. All right. So that's a very important mechanism that 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 when you execute Spark, you don't need to install manually on all the machines. It is the role of resource manager and the entire mechanics that it will automatically install whatever is required. Okay, I hope this makes it clear. So we will continue our discussion from here in the next session. All right, Rajan, please keep this question. This is a very important question, and I would love to answer this question. Okay. All right. I'll just answer a quick question to Robin. What is the alternative .zip file? There is a format called Aljado. Okay, that's what we use. Will data nodes be able to read assigned blocks if compressed file is encrypted? It'll be difficult. We'll have to gather entire data on one machine and so on. It'll be really difficult. All right. So, all right. I hope today's session was useful to you. So I look forward to see you next week. In the meantime, please finish the self-paced exercises. We'll talk about Parquet, and we'll talk about that when we discuss Spark. All right. So the downloader is, I think, KeepVid. I used KeepVid earlier from YouTube that you can use. Okay. All right. Great to have all of you in the session. It was a great set of questions and it was good discussion. So I look forward to see you next week and we'll continue our discussion from the yarn. You can actually start, yeah, you can start with the project. But again, you'll need, the first project is about Hive. So you will need at least that part. Okay. All right. So actually you don't need to go through any other video. It is up to you. So we are here in the scheme. So course overview is done, big data introduction is done, lab overview is done, Linux basics, we have covered basics. So rest is up to you. Java Essential is not required, but if you're interested, you can go ahead. Zookeeper, we finished. HDFS, we have finished. Yarn is where we are. So it is up to you if you if you want to review go through the video as well as go through the exercises, it is up to you. All right. So please, but I would suggest that you make it 100% complete, all of these. That would help you understand the concepts better. Okay. So I would suggest that you go through these up to here at least, or even this one will be useful to you. All right. So I look forward to see you in the next session. Okay. And the projects basically are here only at this place only. So this is one project. Then we have a project Hive project here. Then we have the project towards the end. Okay. This is another project. All right. Let me see if I can also put more projects somewhere as a list. There are 2-3 more works here. This one also has a project on a recommender. You can try that. The recommendation engine is there. And this one also has a project associated. Okay. So, all right. And this one also, yeah, this one has a project. So basically, you just keep on going into these topics sequentially. That'll be good. All right. So thank you, everyone. I look forward to see you in the next session. Bye bye. Have a good day.